Okay, so this is the first video covering material in Chapter 4 for Math 1560 Calculus 1 at U of L for Fall 2017. So in the first couple of sections of Chapter 4, we're skipping the section on Newton's method. We're going to go right into related rates, which is 4.2, then optimization, which is 4.3. So these two sections involve what are, they generally fall under this heading of word problems, right? There's going to be some sort of scenario that we're trying to handle, that we're trying to solve via methods of calculus. And so whenever you're trying to tackle these problems, the type of calculus that you employ in the two sections is slightly different, but there are a number of general procedures that you're going to use in both sections as far as setting up and executing the problems. Okay, so here are a couple of examples of the types of word problems that you might run into. The first one is a related rates problem. Okay, so this is a related rate problem from section 4.2. The second one is an optimization problem, okay, from section 4.3. Okay, so I'll let you guys read the text. I'm not going to read it out to you, but you can see the sorts of scenarios that you might run into. In the related rate problem, you can see that there's a number of information giving you dimensions of various objects, how big things are, and you can see that we have a rate of speed, right? So the person is walking at a certain speed, 400 feet per minute, and in this case, what we're interested in is we're interested in the rate at which his shadow is getting longer, and then we're also interested in a second rate, which is how fast the tip of his shadow is moving, right? So there are relationships between these three rates that you can deduce from the information that you're given. In the second case, we have a pentagon that is constructed as described, and you're trying to optimize the area, right? So for a given perimeter, you want the greatest area. This is typical of an optimization problem. You're trying to maximize a certain quantity, right? You want the biggest possible area, but that optimization problem is always subject to some sort of constraint. In this case, the constraint is that you have to have a perimeter of 30, right? Because if you put no limit on the perimeter, well, you can make your pentagon as big as you want, and you're going to get areas that are bigger and bigger and bigger, right? So to have a kind of a well-posed problem, you need to be talking about greatest area, but constrained in this case by the perimeter of that pentagon. That gives you some sort of limit on the size. Okay, so these are the sorts of problems that we'll be looking at, and whenever you want to tackle these types of problems, there are a number of procedures that generally work no matter what sort of problem you're looking at. Okay, so here are some general strategies. The first one is make sure you've carefully read the problem, and not just once, 2, 3 times. As you read through, you got to identify all the various quantities involved, right? So in the lamppost problem, you got to read through and realize, okay, they're giving you information on the height of the person and the height of the lamppost and how fast the person is walking, and so you have to identify, okay, what are all the quantities involved? Which of these quantities are fixed? Which ones can be changed, right? In the case of related rates, you have things that are kind of changing in time, right? The person's position is changing in time because he's walking at a certain speed. As he moves, the length of the shadow is changing. In the case of the optimization problem, you have one quantity which is fixed, which is the perimeter, one which is variable, the area, and you're trying to figure out, how to make that area as big as possible. It always helps to draw a picture, right? In the case of the man walking away from the lamppost, you probably have no idea how to set that up without a diagram. And this is typical. And once you have a diagram in place, it's usually not so bad, right? The lamppost problem, a useful diagram is going to be something like this. You get your lamppost up here. You draw your person. There's our person. I mean, you can put arms and legs on him if you want, but that's not all that relevant. And so, of course, the light is shining down from the lamppost like so, and the shadow is going to be, well, this region here. That's the region where the light is being blocked by the man as the light shines down. Because of course the light is shining in various directions, right? It's coming out in all sorts of directions from the lamppost, but that's the region where you can't see it. Then you start trying to introduce quantities, things like, well, you might want to introduce something like the distance from the lamppost to the man, because the speed at which he's walking gives you the rate at which that number is changing. You're interested in, let's say, the length of the shadow, so you might want to introduce that quantity. And then you try to think about how these things are related. So if you go back to that problem, the man is 6 feet tall, and they didn't actually tell me the length of the height of the lamppost. I might need that information. Oh, but I can figure it out, because I know that when he's 3 feet away from the lamppost, he casts a 4-foot shadow, right? And so I guess the lamppost isn't known yet, but we can figure that out. We know that this person's height is 6. And one of the things that you might notice here, this is kind of a standard feature, you've got a couple of right-angled triangles. There's a little one, this one, and there's a big one. And those triangles both share this angle, and if they share that angle, then all three angles are the same. So you're dealing with similar triangles, and one of the things that's true about similar triangles is that ratios of their lengths are the same. So if we did the ratio of the length of the bottom side to the left side for the small triangle, that ratio is y over 6, right? For the big triangle, the ratio is x plus y over this unknown angle z. And so they do give us, right, they give us now x and y are, z is fixed, x and y are changing, right? And then by plugging in, they do tell us that even though x and y are changing, there's one moment of time when x is equal to 3, y is equal to 4, I think that's what it was, and that would, you could use that to figure out the value of z, and you could work through, and then you could figure out how to relate the rates at which these quantities are changing, right? So it helps to have a diagram. Once you've got that diagram in place, that diagram is going to lead to an equation, right? Something like this. Where you want to get to is you want to get to an equation that relates your variables, because once you have an equation, then you can start using calculus. You've got variables, you've got an equation, or maybe you've got a function, and then you can start bringing calculus into the picture, okay? So the most straightforward part of these problems is actually the calculus part. Once you've got your diagram set up, once you've got your equation or your function, you've labeled all the quantities appropriately, the calculus part is pretty simple most of the time. I mean, we can come up with difficult problems where it's a complicated function and maybe the derivatives are going to be really difficult, but generally the hard part is the setup. Once you've set things up, the rest is just calculus. You guys are experts at calculus by now. The hard part is the setup. So once you've got the setup, you've done your calculus, you've come to some sort of answer, the only other thing you want to do is you then want to go back and look and say, okay, I've got an answer. What is that answer telling me? Where am I going to use that answer? Because you always have to go back and look at the question again and say, okay, what was the question actually asking me to find? Because depending on what the question is asking you for, if you're dealing with, say, that pentagon one, was it asking for the area, in which case you just give the area? Was it asking for the dimensions? You got to go back and figure out what the actual answer is going to be, right? If you want full credit on a problem like this, you got to make sure you actually answer the question. Okay, so we're gonna see how these strategies play out, first in the case of related rates and later on in the case of optimization, and that's going to be the subject of the next few videos.